Eller dombestemte 900. Så. Jag gör bara som jag ger tillsagt. Fel plats, Claes. Okay. Good morning, everybody, and welcome to today's PhD defense. And welcome both here in the lecture hall and out there in the Zoom space these days, in those strange times. So my name is Dirk Rudolph. I'm the head of division of nuclear physics, and amongst others, then this implies that I have to chair, or that I'm happy to chair, these PhD defense acts. And before I'm going to explain a little bit on how the procedure is, I would like to first introduce the main people of interest as of today. So first of all, I would like to very warmly welcome Per-Erik Tennier, our faculty opponent from Stockholm University, who, again, in these strange times, did the extra effort in actually driving down all the way from Stockholm. So thank you very much, Per-Erik, for actually being here in person these days. Secondly, we have the respondent, Alexander Knязев, who is going to defend his thesis entitled Reactions with Radioactive Beams and Development of Scintillator-based Detector Systems today, this morning. Hopefully by lunch it's going to be done. Then we also have the evaluation committee, and two of the evaluation members are in the lecture hall. So we have Dr. Oksana Smirnova from the Division of Particle Physics. We have Dr. David Silvermuir, also from the Division of Particle Physics. And then remotely, we are happy to have with us Ann-Cecile Larsen from the University of Oslo. And as a backup, just in case eventually you drop off, the somewhat more senior Professor Magne Guttormsson, so to say, again, just in case, and he is also with us via Zoom today. And then I should not forget to also mention the supervisors of Alexander, primarily Joachim Sederschell, who is the main or has been, or in a sense still is until the near future, the main supervisor of Alexander, and Pavel Golubev, who has been the co-supervisor. And that concludes the main people, so to say, in action this morning. Then to the procedure, yeah, first going to listen to a presentation by the faculty opponent, who is going to introduce us here in the lecture hall and you remotely into the topic of the thesis. Then after that presentation, we will listen to a presentation by Alexander, who is going to tell us what the main achievements of his thesis work or his time in Lund in our division has been. After that, we are going to take a short break, bensträckare in Swedish. And after that one, we are going to reconvene. And then at first, the faculty opponent and the respondent, they will have their discussion about the thesis and the contents of the thesis. Prior to that, then the evaluation committee will be asked to ask questions, or in case they are still wondering about things, those are the ones being called up one by one, including eventually our backup in Oslo as well. And then the word is going to be free for everybody in both the physical audience and in the video audience. And for those of you who are connected remotely, if you are in the Zoom meeting, there's this Q&A button. So later on, once there's the open call for commenting, then don't hesitate to put something into the Q&A section in the Zoom meeting, and I will then try to read from the computer here and then convey the question, presumably primarily to Alexander, in case there is anything from outer space, so to say. Okay, and then afterwards, after the discussion and the questioning has been concluded, then I would like to ask the faculty opponent and the supervisors, but primarily the evaluation committee, into the neighboring seminar room here. And there will be another Zoom meeting where we will connect in our remote members of the evaluation committee also in that room, where then you're supposed to discuss the performance and the quality of the PhD thesis and take the final verdict afterwards. Okay, having said all this, I will sit down and I'll give the word to Pierre Tenier, our faculty opponent, to give us an overview of the topic of the thesis.
Thank you very much, Rudolf. Let's see, I have a presentation here, which I will try to start. It's there, but it's not here. Why don't I see it on my computer? Or perhaps I don't have to do it, I don't know. Okay, so first of all, I would like to thank the Faculty of Science for inviting me, taking part in this important occasion. I look very much forward to discuss the work of you, Alexander, with you later. I will start with, I don't know, perhaps could you help me to get my presentation forward here on the screen? Why don't I see that one? Is it because I'm not zooming? Aha, okay, I think I know perhaps. No, I perhaps I could do it. Thank you very much. Okay, so I will, in this presentation, I will try to put the work of Alexander into a broader context, and I will actually start with a quite general question here, which is this one: where do we come from? Of course, this is quite philosophical issue, perhaps, so we have to perhaps focus on some more details, which could be these questions. What are we made of? What is the Earth made of? What is the solar system made of? And what is the matter around us made of? And actually here I would have had actually a small, nice saxophone solo. But you can see perhaps the names of the persons. Okay, yeah. Actually, that was the song that I would have liked to hear. And this could be a quite general answer to these questions, but of course it doesn't explain anything. I mean, but in principle, we believe that we all the matter comes from some kind of stardust that was created some time ago. So a more detailed question could then be, when, where, and how were the building blocks of matter, the atoms, created? And of course, the work by Alexander is focused on the how question, of course. I mean, to try to understand and determine how things were created. But anyway, I've started here to make this kind of popular. Everybody here in the audience, I think, is aware of these things, but perhaps some are not. In order to understand this where and when question, one of course has to go back to the Big Bang some 14 billion years ago. There is a more exact number nowadays than this, but and sometime after the Big Bang, say 30 minutes after that, we believe that the universe consisted of protons, alpha particles, and electrons as matter particles. Some short time after that, 10 million years, these protons and alpha particles, they combined with the electrons. It was possible because the temperature was so low. So neutral atoms were created, like hydrogen and helium atoms then. So at this stage, one can say that the Big Bang accounts for, well, the most light particles or the most light atoms that exist in the universe, namely hydrogen and helium, and also to some extent lithium. So where do the other atoms, the other elements come from? I mean, like carbon, which is of course essential for our life, and oxygen, and some heavier things like iron and gold, and all the other here in this periodic table, which you know. Well, some of them perhaps don't exist on Earth right now, but many of them do. Most of them do actually in this table. Well, yes, as you know, these neutral atoms, they form gas clouds, and under gravitation they form stars. And at some point, due to this gravitational attraction, the temperature increases and nuclear reactions will take place that will form then heavier atoms or heavier nuclei in principle than protons and helium. For instance, in the first step, carbon. Okay, so looking at this chart of nuclides, which is also present in Alexander's thesis, we see that there are many nuclei existing, which are these small squares in this diagram. And then there are also areas, these light blue and some kind of light red, where we believe atoms or nuclei exist. So the question is, how are all these now created? The black dots here on the screen are the stable isotopes of different elements, and they are present at Earth, in the crust of Earth. So as we said, before the era of stars, only the lightest elements in the lower level, left-hand corner are present. In the stars, there is a processes of fusion, as I said, nuclear reactions that will create atoms or nuclei then up to something like iron. And there is also these kind of slow processes in the stars that will form nuclei up to, but not further than lead or perhaps bismuth as well. It's a long-lived isotope of bismuth. But that explains, in principle, the nuclei along this stability line, along, I mean, those nuclei that are in black here. in principle. So what is needed to create the rest, we believe, is some catastrophic event for the stars, namely supernova explosion or the merger of neutron stars. That those catastrophic events will create, in principle, all possible nuclei, we believe. And in the case of our solar system, this happens a couple of, perhaps exactly how many, but I mean, the Earth was created something like 5 billion years ago. So before that, these events happened in the close vicinity of the solar system. Okay, so in order to understand, I mean, we said that, okay, we come from stardust, but we have to know in detail how these processes go on in order to really understand in depth what has happened. Which means that we have to understand the properties of these nuclei that take place in these events. And most of those nuclei, they are unstable nuclei. So we cannot just dig them out from the ground and look at them. We have to create them somehow. This is in principle the aim of Alexander's thesis in some kind of wide scope, to create the possibility to study these kind of unstable nuclei in order to understand, for instance, the element synthesis processes. You discuss, or Alexander, he discusses in his thesis how these unstable nuclei can be produced, and you discuss two facilities, Isolde and FAIR, and also GSI, of course, you discuss. But Isolde and FAIR are perhaps the future facilities for these things in Europe. The thesis of Alexander is, I can say, divided into two parts. So one is the experimental study of the nucleus carbon-15 at Isolde. Carbon-15 is an example of a quite peculiar kind of nucleus, a halonucleus, which means that there are, in this case, it's one neutron, and it can also be two neutrons that exist on the average very far from the center of the nucleus. So it's in the, I mean, in principle, they exist in a region where they are not allowed in classical mechanics because they have, in principle, negative kinetic energy, so that is not allowed. But in the quantum world, this is perfectly okay. The second part, which is, to my understanding, is the main part of his thesis, is this very ambitious and detailed investigation of the instrument CALIFA, which is then developed for these kind of studies and will be placed at the FAIR facility at the R3B experiment. And here he discusses in detail, as I said, these investigations about the crystals that are used in this calorimeter, cesium iodide, the doping, how that affects the properties, the crystal shapes, the treatment of the surfaces, how you read out the signals, what about the noise, and more things. So it's a very interesting and detailed investigation of these things. I will just go just for 1 minute to another experiment to show that these things are done in a similar way, and of course very important to do in all these kinds of experiments in nuclear and also in particle physics, to understand the instrument and to make the instrument as good as possible. This is the PANDA experiment also at FAIR, where I take part, so to say. And we have done very detailed studies, but not to the same extent, I must say, of another scintillator material, PWO, which is lead tungstate, actually, in the chemical form. And here you can see one of our investigations about the light yield as a function of where the gamma ray hits the crystal, which is an important part also of Alexander's thesis. And we see that there is a light yield non-uniformity along the crystal length, depending on the shape of the crystal. And one of these cases is quite extreme, actually. It's a huge non-uniformity of the light yield, actually. I will not dwell into this very much, but I mean, doing this kind of work, it meant that I, together with my colleagues, we had to be here in Lund, actually. And that was, of course, very pleasant. I think we had perhaps 10 occasions where we made measurements at the old MaxLab facility, Max4 facility, at the tagged photon facility in Lund, to measure the resolution of these system of PVO crystals. And you see that this is one to the left. We have our crystal set up in a cooler at minus 25 degrees was the temperature that we wanted to reach in the lab, and there is a mirror picture of our two collaborators there. And we also had some time for sightseeing as well, as you can see. And one example of one result is the resolution, as we call it, as a function of the photon energy. You see the black curve, for instance, where the photons hit the crystal in the center, and the other curve with worse resolution, where we hit with the photon beam in the corner of the crystal, I mean, where four crystals meet, so to say. And you can see that this is a completely different energy range compared to what Alexander has done. This is 10 to, well, 60 mega electron volts. And we see that the resolution is also quite bad compared to what Alexander has done. But of course, it's a different, so to say, aim of the experiment in that sense. Okay. I think that in his thesis, Alexander shows the crucial importance of developing instrumentation. It's really needed. And unfortunately, I would say, so this is kind of statement, this is not often so visible to the public or the other, the science community. And it's not so appreciated, actually, unfortunately. But I think it's extremely important, and it's an important work. So thereby, I leave the word to you, or to you, yeah.
All right.
Okay.
Mm-hmm. All right, excellent. Now let me just check if I can see my presentation here. Excellent. Yes, thank you for the introduction. Thanks to the committee for taking on the task of evaluating these thesis. Then I'm going to talk about my work here for the past 4.5 years, which concerns reactions with radioactive beams and development of the detector systems for them. I'm going to start with one moment. Yes, sorry. Sorry for that. Yes, I'm going to start with the motivation. Why do we use radioactive beams and how we produce them? I'll exemplify it with the low energy scattering experiment with carbon-15 to investigate its halo structure. I'll continue with the detector development for a high energy experiment. And then I will conclude with outlook and results. Today we know of existence about 2,000 radioactive isotopes, mostly in the neutron-rich region of the nuclear chart. And in total, we believe that there should exist about 7,000 of them. The neutron-rich region of the map is of special interest for us, and in this region we can study such phenomena as neutron halos and evolution of shell structure of a nucleus with respect to its isospin. Now, the shell structure of a nucleus can be exemplified with its single particle states calculated for a given potential. Here you can see results of calculation with a simplified Nielsen's model for a spherical nucleus. Experimentally, the single particle states above the Fermi level can be investigated with the transfer reactions, and the states below can be studied with nuclear knockout reactions. Typically, we use the isol-produced beams for transfer reactions and the in-flight produced beams for knockout reactions. Both of these techniques of producing the radioactive beams have their advantages and drawbacks. For example, with isol-produced beams, we can get the highest quality of the beam, and the in-flight produced beams give us an opportunity to work with isotopes with shortest possible half-life times. Now, in the scope of this thesis, we were using isol-produced beam of carbon-15 to investigate its halo at low energy scattering. The halo phenomenon as such was first discovered by Isao Tanihata in 1985. Here you can see the density distributions of the valence nucleon in S state on the left and P state on the right, calculated for different separation energies. Experimentally, the halo phenomenon manifests itself in large reaction cross-section, narrow momentum distribution of the valence nucleon, and in increased cross-section of electromagnetic dissociation. Today, about 17 halo nuclei have been discovered so far. And for us, within the scope of the thesis, carbon-15 is of special interest because it is believed to have the valence neutron in S1/2 state. Now, looking closer to the motivation for a low-energy carbon-15 experiment, we can say that the halo structure of carbon-15 has been earlier investigated at energies above 100 MeV per nucleon. And interestingly enough, it has been reported that the increase in the cross-section is not as prominent at relativistic energies. This was attributed to a decrease in the breakup and the transfer probabilities. The relatively low neutron separation energy in this nucleus leads to a strong dependence of the shape of angular distribution on the reaction mechanism, even at low energies. And thus, we can say that a low energy experiment can provide us with an additional information of the halo of carbon-15. We have performed such an experiment at High-Zolde facility, where we used a calcium oxide primary target to produce a beam of carbon-15. The beam was accelerated to 4.4 MeV per nucleon and scattered on a lead target, which was mounted on the XT03 beam line. The intensity of the beam on the target was about 10 to 5 particles per second, mostly nitrogen-15 with 3% of carbon-15. The nitrogen and carbon events were separated with particle identification plots, which I will show a bit later. The angular distribution in this reaction was measured with the Gloria setup, which consists of 6 delta EE double-side silicon strip detectors. A sketch of this setup you can see on the top right corner of the slide. The beam on the sketch enters from below and scatters on the target in the center of the setup. The setup covers the angular range from 15 up to 160 degrees, and the angular distribution of the setup is about 2.5 degrees. You can also see some additional parameters of the setup. Here, some preliminary results of the analysis presented. On the top, you can see the heat patterns from the two forward telescopes. One of the strips in telescope A was malfunctioning during the experiment. And on below, you can see the particle identification plots used to separate the carbon-15 events from the nitrogen-15 events. From the separated carbon-15 events, we have reconstructed the angular distribution, which is shown here, which we can also compare to the angular distribution in scattering of carbon-12 on the same target, which is shown there. In different colors are shown some theoretical predictions of carbon-15 scattering before any experimental data at low energy has been available. Yes, so from the results of the angular distribution, we have extracted the total cross-section of the reaction, which was found to be 3000 millibar. Together with the parameters of the optical potential. The significant total cross-section together with rather large imaginary diffuseness points towards a significantly extended neutron halo in carbon-15, which can be compared to a well-established case of helium-6 nucleus, and thus corroborates the results from the high energy experiments. As I mentioned before, I also worked with high energy radioactive beams. More specifically, I was involved in detector development for the R3B experiment. The R3B experiment is a part of New Star collaboration at the Facility for Antiproton and Ion Research in Darmstadt, Germany. The collaboration consists of three major branches. The high energy branch is of the most importance for us, which will be exploited by the kinematically complete measurements of reactions with relativistic radioactive beams. The R3B experiment can be separated into four major parts. The trackers of the reaction products, the calorimeter Khalifa, the superconductive magnetic GLED, and the neutron spectrometer Neuland. The components of the experiment are being mounted at the moment. Here you can see the current state of the mounting procedure on top, and below you can see some major components of the experiment, like the neutron spectrometer Neuland, one of the prototypes of the fragment trackers, the GLED magnet, and more importantly, the Khalifa calorimeter, which one of the major focuses of this thesis. The Khalifa calorimeter itself can be also separated in different parts. Most important are the barrel part, the IFOS part, and the SEPA part. One interesting feature of these calorimeters is that it is designed to work in two different modes, specifically the calorimeter mode and the spectrometer mode. And for each mode, there is a number of completely different requirements. So in the calorimeter mode, we care about the photopeak efficiency and also about the stopping power of the material of the detector. And in the spectrometer mode, obviously, we care about the energy resolution, So for gamma rays, we expect energy better than 7% at 1275 keV. And for the detected protons, we expect energy resolution about 2%. The set of requirements to the calorimeter itself drives the geometry of the modules of the setup to a certain shape. So the length of the detector modules arises from the stopping power of cesium iodide selected as a scintillator. And the aperture of the detector modules arises from the fact that we need to perform the Doppler correction of the Lorentz boosted gamma rays. And also from the fact that since we aim to measure the gamma rays with energies up to 20 MeV, we need to consider also the development of electromagnetic showers. To perform an accurate add-back procedure of these showers, we need to reduce the amount of that material between the detector modules. So this is the result of the interplay of these requirements. So the detector modules, they have an elongated finger-like shape with lengths from 17 centimeters up to 22 centimeters. This is how the detector modules look in real life. In the middle, you can see an avalanche photodiode, which is used as a light sensor in our detector modules. The detector modules are grouped in sectors, and the sectors then complete the shape of the calorimeter. Here on the right, you can see a testing routine for a couple of such sectors being prepared for a test experiment. Now, since we use large volume scintillators, we need additional knowledge concerning the correlation between the non-uniformity of light output and the energy resolution of a detector module. We need also to investigate the contribution of thallium and homogeneity to the light output non-uniformity. And with these data, it is of interest to perform simulations of light transport in these large volume scintillators. Also, for these simulations, it is necessary to determine the material parameters and also to evaluate the uncertainties of these parameters. Now, looking closer at the light output non-uniformity in the large volume scintillators, we can say that there is a number of sources of light output non-uniformity. Most important of them are the shape of the scintillator and the light absorption length of the medium. The tapered shape of the Khalifa modules gives rise to the focusing effect, where the scintillation light from the most distant parts of the scintillator are detected by the photosensor at the angles closer to 90 degrees. The interplay between the focusing effect and the light absorption length, which is in our case comparable to the total length of the detector, results in characteristic light output curves showed here. The light output curve can be evened out by applying the surface treatment to the lateral sides of the detector module, thus increasing the energy resolution. There's also a number of additional characteristics of the detector modules which we need to investigate in order to better understand the performance of the detectors. So those characteristics are the efficiency of the add-back procedure, again, gamma rays up to 20 MeV. We need to consider the electromagnetic showers together with the Compton scattering. Also, since we use avalanche photodiodes, we need to investigate the temperature stability of the detector models. And also, it is of interest to quantify the contribution of noise into the overall energy resolution. But already now we can say that those characteristics, those parameters, they have a limited influence on the overall energy resolution. Now, going back to the relation between light output non-uniformity and energy resolution, to investigate it on a larger set of Khalifa detector modules, we have designed and constructed a testing station. The testing station consists of 2 stepping motors in X and Y direction. The stepping motors move the scanning head with 2 collimated ports for gamma ray sources. The crystals inside the testing station are being scanned in 10 equidistant points, and the photopeak position in these points is being registered. The light output non-uniformity is then defined as the difference between the highest position of the photopeak and the lowest one, normalized by the average. Here you can see the influence of the light output non-uniformity on the energy resolution of the photopeak. The wider is the distance between the individual photopeaks, the wider becomes the total photopeak, and hence the resolution becomes worse. We can also see this relation in the correlation plots of light output non-uniformity and energy resolution measured with an uncollimated source at a different energy. And indeed, this correlation was found to be the strongest one amongst the set of other characteristics also measured with our testing station. We have also found out that there is a noticeable correlation between light output non-uniformity and normalized efficiency. And these can be explained in a way that the wider becomes the photopeak, the more events we lose in the shoulders of the photopeak into the background. Now, the correlation analysis also allowed us to extract the best attainable energy resolution of the sample, which was found to be about 4.5%. The average resolution of the sample was 5.2%. We can now also need to establish the contribution of the inhomogeneity of thallium concentration in the module into the total light output non-uniformity. And for that, let me just briefly remind you the scintillation mechanism in inorganic crystals. So when a particle is scattered in the scintillation medium, the conduction band is populated by electrons from the valence band. In some cases, the electrons in the conduction band can form a loose bound to the holes in the valence band. In such cases, we talk about excitons. Both free electrons from the conduction band and excitons can be trapped on impurities of the crystalline lattice, and the excitation on the impurities results in the scintillation flash. The ratio between free electrons and excitons depends on the charge number of the ionizing particle, and thus we can perform pulse shape analysis for particle identification. An example of such analysis I will show later. Now we also know that not only the shape of the emission peak, but also the total amount of light in a scintillator depends on the concentration of the dopant. Even worse than that, we know that some particular features of the manufacturing procedure can influence the light output, resulting light output depending on the procedure itself, such as, for example, the growth atmosphere and the pooling rate. After the manufacturing, the spinodal decay of the solid solute of the dopant in the crystalline lattice can also result in the inhomogeneity of the dopant in the scintillator. An indication of that we think we saw in the in our light output non-uniformity measurements. So, for example, we found out that there is a reduced number of crystals with light output non-uniformity less than 3%. To investigate it closer, we have selected test sample, which was measured for its light output non-uniformity, both in the polished state and the lab state. This data was also later used for the simulations. So this sample was irradiated by a proton beam in 10 equidistant points, and the characteristic X-ray spectra in each point was measured. From these characteristic spectra, we have extracted the concentration of thallium in each point, and also we have extracted the average concentration in the scintillator, which was found to be 0.84 per mil. The distribution of the concentration in the crystal was propagated through the light output curve. This light output curve was measured by the manufacturer on a similar type of the crystals. So from the propagation of the distribution of the dopant concentration through the light output curve, we have extracted the light output non-uniformity, which was found to be 4.6% with a noticeable uncertainty. The uncertainty here arises from the uncertainty of thallium concentration in the medium. For the future experiments, we have also investigated the relation between the uncertainty of thallium concentration and light output non-uniformity. Nevertheless, the extracted light output non-uniformity we have used to investigate the increase of the total light output photopeak. And from the simulations, we have found out that the increase is about 0.5%. We can also compare it to the actual measurement, and from the actual measurement, we have extracted 0.22%. Again, this discrepancy we attribute to the uncertainty of thallium concentration. A number of other characteristics was measured as well, as I previously said. We have investigated the efficiency of the ADVEC procedure. Also, we found out that the gain of the APDs is stable at the operating temperatures, and we also quantified the contribution of noise to the overall energy resolution. Now, with all these characteristics parameterized, we can finally perform simulation of light transport in large volume scintillators of the Khalifa model shape. Let me just briefly remind you what is of interest in these simulations. So we need to take care about the light absorption in the medium, and also to the details of light scattering and at the boundaries, together with the details of propagation in the Kepler medium. Now, the light absorption length was measured by a commercially available spectrophotometer. In the spectrophotometer, we were measuring the attenuation in the crystal as a difference between the sampling beam and the reference beam. From the attenuation, we have extracted the light absorption length, which in our case was found to be about 34 centimeters in the region of the emission peak of cesium iodide doped by thallium. The details of scattering on the boundaries of the scintillator was simulated with the surface maps, surface height maps. For that, we used a commercially available atomic force microscope. A small sample of cesium iodide was prepared for that. The surface of the sample was treated by the specialist from the manufacturer of the crystals the same way as during a production run. The surface maps we used to produce lookup tables of the reflected and transmitted angles together with the reflectivity curves. Before we perform the simulations, though, we need to measure an actual performance of the detectors with respect to lapping. So for that, we were increasing lapping of the crystal stepwise, and in each step, the light output curves were measured. The same then was performed during the simulations, and albeit we did not reproduce the total light output in our simulations, the trend was reproduced rather nicely. So we get we get lower light output non-uniformity with the increased lapping area. The use of lookup tables in our simulations allowed us to reduce the total number of free parameters in our in the simulations. So with that, we can focus on investigation of the sensitivity of the results to the actual physical parameters. We have selected 3, or rather 4 such parameters, like reflectivity of the SR foil used as a reflector in our measurements in our modules. The light absorption length and the refractive indices of the window and the coupler. So we have found out that the result is most sensitive to the reflectivity of the SR foil, followed by the refractive indices of the coupler and the window. Surprisingly, the sensitivity to the light absorption length was found not as prominent. So that was the performance of the individual detector modules. And now it is of interest to look at the performance of the assemblies of the modules. I personally was involved in 2 such experiments, one in cyclotron laboratory in Krakow and another one in JSI. In Krakow, we were investigating a number of targets with a P2P reaction, and in Darmstadt, we were investigating the correction routines, so the Doppler correction routines together with a few physics cases. So here are presented some results from the Krakow experiment. Top left is the the standard delta E particle identification plot, which you can compare to the right to the particle identification plot from the pulse shape analysis. And on below, you can see the extraction of the elastic channel on scattering on the water target. These plots were used to investigate the energy resolution, or sorry, angular resolution of the assemblies. This is one particular thing I personally quite proud of. In our Krakow experiment, we have investigated P2P reaction on oxygen, and in the results we have resolved the 3½ minus to 1½ minus transition, both in the proton spectrum and the corresponding gamma ray spectrum. So finally, a first physics experiment of the with most of the R3B components set in place was performed rather recently, this February. The isotopes of calcium were investigated in P2P reactions in inverse kinematics to investigate the evolution of the shell structure. With that, let me conclude. So first of all, we have investigated carbon-15 in a low energy experiment. In that experiment, we have corroborated the results from a high energy experiment. More precisely, we have established the halo structure. And for a high energy experiment, some detector development has been performed. Most importantly, we have established the empirical relation between the energy resolution and light output non-uniformity. We have also investigated the contribution of the non-homogeneity of thallium distribution into the overall light output non-uniformity. We have established the contribution of noise to the energy resolution together with the stability of the gain of the modules. The efficiency of the add-back procedures was investigated as well, and most importantly, the simulations of light transport in large volume scintillators was performed together with the sensitivity analysis of some physical parameters. With that, let me conclude this talk, and thank you for the attention.
Okay, thank you both Erik and Alexander for the nice presentations. And as I indicated before, it's now time for a short break. And they managed the timing in that respect very nicely, so that we are going to reconvene at 10 o'clock sharp for the discussion session afterwards. So again, short break, and then we reconvene. Okay, as far as I can see, at least in here, all the relevant people are back in the lecture hall, and I hope that also our two guests from Norway or members of the committee from Norway are online again. And thus I will hand the word over to Per-Erik again to start the discussion with Alex. And then again, once the opponent is happy, then we will open the questioning first towards the committee members and then to the public. And eventually, I mean, it was quiet before the break, but also remind to, in case you have your mobile phone with you, to turn it actually off. Small anecdote, if you're playing chess and your mobile phone rings, you lose the game. So we don't want any mobile phones here to ring, please. So,
yeah.
Oh,
thank you.
Yours.
Yes, thank you. So Alexander, I will discuss your thesis with you. And my idea is to go through it from the first page to the last page in principle, to some extent. Perhaps with some deviations from that. But you, I mean, you have an introduction where you sort of say define the physics that you're interested in, and also discuss about beams of unstable nuclei. So one thing there, I mean, you discussed the pros and cons with the in-flight and the isol method. So for the isol method, you gave a number for in principle, the lowest half-life that you can study, so to say.
Mm-hmm.
At least in your presentation, you did that. What about the in-flight technique or at the FRS? I mean, what would the limit be? Or what defines the limit, so to say? What?
You're talking about the half-life times, or?
But
you're talking about half-life times.
Yes.
Yeah. Well, it has to do with the time needed to get to the physical target, together with some additional peculiarities. So from what I remember, the theoretical limit is something about nanoseconds. I mean, of course, when we apply the physical limitations of actual setups, we go to a few microseconds, maybe below microsecond, but better than that, not with the current existing experimental setups.
Okay, thanks. You mentioned for the FRS that you may have, for instance, you have noble gases in the beam. I mean, in the primary beam, I think. And you, I mean, just a small reflection. You said you have noble gases from argon to xenon, which means that how many noble gases do you really have?
Argon and xenon.
Yeah, there is one in between also. Okay, it's not. I mean,
neon.
It's krypton, I think.
Oh, sorry. Yeah.
So it means, I mean, when you say from argon to xenon, it means that, I mean, there are three actually. I mean, one could imagine, okay, there are many when you say it like that. But
one could hope for tennessine. Oh wait, sorry, agoniston at some point. But
yeah. Okay, but yeah, that was a small detail. Then of course you plan to work or put this machine or this instrument at the super FRS. What would be the improvements compared to the present FRS?
An excellent question. Yes, so the major improvement is that the energy of the beam. So you need much larger magnetic systems like lenses and dipoles and stuff like that. Yes. So another improvement is the acceptance, emittance. Sorry, emittance of the energy of the resulting radioactive beam. More details, I'm not sure if I can provide.
But this also means intensity. I mean,
oh yeah, well, I mean, of course, yeah. That's the whole point. Yeah.
Yes. And perhaps also the range of.
Yes, that's the thing with the radioactive beams. especially the high energy radioactive beams. With high energies, we can use much thicker targets. Yes, and even though we lose the we lose the emittance, or rather get the emittance of the beam, we can fix it with some particular techniques, like I don't know, like particular shape of the lenses or something like that. Yes, but one good thing is that the higher the energy, the thicker is the production target, and the larger is the intensity of the radioactive beam. Yeah.
Would you also utilize thicker secondary targets?
Absolutely, absolutely. Yes. Well, for that, I mean, there is also a few nuances, so to say. So the thicker is the production, the physical target, the more uncertain is the momentum of the produced nuclei, and for that we need to employ a rather sophisticated tracking system, which we do have in our R3 experiment.
Thanks. Also in the introduction, you are discussing halo nuclei.
Mm-hmm.
And you also discussed it here in your presentation. Yeah, I wrote down here why I call them halo nuclei, but I think, I mean, in principle, you have discussed that. I mean,
yes. Well, what in particular of interest for you?
no, I mean, what? Yeah, but why do you say halo? To say.
I guess one maybe not a good example is a galaxy halo, maybe. So there is a distribution. There is a distribution of probability of finding a nucleon at a certain distance from the actual surface of the core nucleus, so to say. So that's why we are talking about a halo, a nucleon halo.
You give some examples of, I mean, or you write down a wave function for the halo, well, particles, the halo neutrons outside the, so to say, the core, or outside the which is an exponential in principle in the radial coordinate, which is then a principle just exponential because there is no potential out there. Is it? So interpret that. I mean, it's equation 1,1 where you write down the wave function.
Yeah, well, they are still loosely bound. I mean, it's not a free nucleon. There is still dependence on the separation energy.
On the potential inside, yes.
Yes,
the core, yeah. But the wave function here is for, in principle, for a nuclear for a neutron outside the
yes.
I mean, the constant, so to say, zero potential. Yeah. Let's see. Yeah, you write. Yeah, in figure 1.2. Yeah, figure 1.2. You showed it also in your presentation. The densities of these valence neutrons in two different states. I just wonder. The first to the left, you say that it's an S neutron, and you call it the 1s state. This seems quite confusing to a nuclear physicist.
Yeah, well, okay. That might be a typo, actually. It's not necessarily 1s state. It depends on the nucleus, of course.
Well, probably it cannot be what we normally call the 1s state. I mean, the lowest S state in the shell model, because then there would be.
Yeah, for sure. It is not the lowest one. I mean, absolutely.
No.
Yeah.
So
it is an NS state, not 1s state.
No, yeah. It's probably 2s.
Yeah. Yeah, 3.
How would I see that? Why can I say it's probably the 2s state?
1s state would be helium. So.
Yeah, but I mean, from what it looks like, the distribution.
Well, we see this the drop in the
the nose. Yes.
Yes.
Yeah. Perfect. And at same to the right, we would call that a 1p state, I think,
Mhm.
in the normal way to
Mhm.
denote the states in the
Mhm.
shell model.
Mhm.
I suppose here you're right, 0p state.
All right.
Which is, I mean, it's a counting of nodes. I think these
Yes,
numbers.
yes.
Yeah.
There are different approaches, unfortunately.
Yes. Good. Let's see. Yeah, I mean, I will continue to somewhat more with the halo nuclei. You're right on page 7. In the on the middle of the page, you write another characteristic of a halo nucleus is a narrow momentum distribution. Writing it like this, it seems like this would be some kind of independent property of the wave function or this neutron state, independent from the extension of the in space of the.
I would say it is more related to the experimental techniques. So when we investigate halo nuclei, it is more precise to extract not only the total cross section but also the momentum distribution. And so far we can say that each halo nucleus has a narrow momentum distribution. So hence we say about the property.
Yes. Yeah, so the experimental thing to look at is then perhaps the momentum distribution. Could you from that calculate the spatial distribution if you have measured the momentum distribution of this neutron, for instance?
In principle, yes. In a way, we could relate it to the Heisenberg uncertainty or something.
Good. Yeah, that was exactly what I wanted to hear. Actually. No, of course, there is a close connection between the two. I mean,
Sure.
If you know one, you know the other in principle. So they are connected. So I think, for instance, equation 1.5, if you would put in the uncertainty in space, which is related to this k, in principle, you get the thing that looks like the Heisenberg uncertainty principle by just rearranging in equation 1.5, actually. Good. Let's see. Yeah, there is. Well, yeah, I have at some equations or in some discussion in your thesis. I'm not worried, I would say, but there is some perhaps about units. I mean, confusion sometimes, or that you have. It's understood that you are not using h bar or put it to 1 or something like that. Or
in some cases.
in some cases,
yeah.
yes, but it's not evident perhaps where you do it.
Yes, all right.
Okay, but I mean, for instance, equation 1.4, you have p squared plus k squared.
Yes, yeah, sure.
For instance.
Here I omit h bar and c.
Yes. Okay. Well, one should be aware of that. Some places it's really like that. Okay. Yeah, let's move to. Okay, I've written here a question. Yeah, perhaps I will come back to that. But when you're discussing the properties of your detector that is needed, I mean, there are many things. I mean, the resolution, for instance, is an important thing. But you do not discuss problems that could be connected to rates. I mean, that you have high rates of particles or photons into your detector. Is that not a problem?
For radioactive beams, it is not a problem. Especially for the colorimeter, since we are talking about scattering of a radioactive beam, which is itself has a rather limited intensity. So Yes, and in principle, okay, scintillator is not a very fast detector, but should be enough for the intensities we care about.
Okay, I will come back to the scintillator. Yes, but yeah, I understand that when I read this, that it's not a problem, so to say, the rate. Okay. What about chapter 2? I will not go into so much details there, but I still has a problem. Well, I don't have a problem with the units, but perhaps you can. I mean, for instance, the figure 2.1, where you show the shell model calculations from the Nilsson model. I mean, in the spherical case, where you start from the harmonic oscillator, as I understand. And then you add some terms. When there is an L squared, for instance, an L squared, I mean, there's L dot S and L square. What, if you would calculate that L squared in, for instance, the 1p state, what number would you put in to this equation?
Yeah, well, it would be H bar squared.
What would you say?
H bar squared. Well, I mean, we measure. We would measure it in units of H.
Yeah, but here it's without. I mean, here it must be without units since n is without a unit.
Yeah, sure.
So yeah, okay. So the absolute value of the orbital angular momentum would be L times L plus 1, I suppose, then the quantum numbers.
Yes, okay, yeah, sure.
I mean, that
yes,
is. I mean, in practice, you have to put in a number if you want to use this equation or this.
Yes. So yeah, in that respect, yes, the L squared we would measure as L times L plus 1.
Yeah, good. Perfect. Yeah, then I'm actually jumping to page 2.5. No, figure 2.5, where you, there's a figure there. An example of a P2P reaction on lithium-6. Can you, I mean, you don't discuss this very much, but can you say something about what we see or what we are supposed to notice in this figure?
All right, so we are talking about the top or the bottom.
We can start with the top.
All right. Yes, in principle, what we believe is the single particle states in lithium-6. Measured with respect to energy. So that would say that we get the first single particle state on the surface and the second one below.
Yeah, these are the two peaks, so to say.
Yes.
Yeah.
So yes, and then we just compare it to the what is it? The angular distributions, corresponding angular distributions. The each respective peak to the each respective angular distribution.
Yeah, and there's a difference in the angular distribution in these two
Yes. So
states, so to say.
Yeah, that would be the difference between the angular momentum of the single particle states.
And the narrowness of the distribution. That's.
Yes, sure. But
is that an important thing here? I mean.
The narrowness, yes, the narrowness we can relate to the energy separation.
And also perhaps to the momentum.
Yes.
Mm. Okay, so would it be correct to say, I mean, that the angle distributions are more narrow in the right-hand picture, meaning that the momentum distributions are also more narrow for that state closer to the surface?
Yes, and indeed we see that yeah, absolutely, the state which is closer to the surface has more narrow momentum distribution compared to the state below the surface. So,
yes, yeah. Good. I will go on to chapter 3, because now we're coming closer to the things that, I mean, is the main topic of your thesis, the properties that are important to fulfill, so to say, for your detector. You talk in the beginning about the energy resolution for gamma rays. I mean, since you have many plots and where you show the energy resolution in terms of percent, how do you define the energy, this number, the energy resolution? How do you define it?
It is, yeah, it's in a standard way. We compare the full width of maximum to the center to the Gaussian.
Good. I mean, yeah, because there may be other ways.
Oh yeah, sure.
Yes. Yeah. I mean, in the plot I showed in the beginning, it was actually the standard deviation of the the curve divided by the energy. So.
Well, okay. I mean, in the whole thesis, when we talk about resolution, it is always about the full width half maximum.
Yes. And in the beginning there on page 23, you compare some different detectors. For instance, high purity germanium detectors with a scintillator detector, which is lanthanum bromide detector, and you say something about the resolution. In the first case, you say 2 keV, which is then probably 0.15% in your way to discuss resolution, I think. And then 2.9%, but that's slightly different energy, half the energy for lanthanum bromide. And then you say that, okay, one can understand this kind of difference. I mean, 0.15% and 2.9% then, in terms of the energy needed to create electron hole pairs or created, I mean, photons in the scintillator. And then one should compare the 2.96 electron volts with the 10 electron volts. I mean, to me, if we would use the number 2.96 and 10 electron volts respectively, the difference in resolution perhaps would not be that large as you think.
Yes, we need to also take into account the efficiency of the collection of the energy carriers. Sorry, information carriers. So in scintillators, it is much worse.
Yeah, I mean, for germanium, there is something called the Fano factor normally that you introduce is when if you want to use Poisson statistics, for instance, and you have to introduce this Fano factor in order
sure.
to make the resolution better, actually, compared to the Poisson number.
Oh yes, in scintillators, it is the other way around.
Yeah. Yes. Yes. Okay. Good. Yeah, in the case of cesium iodide, is the number of produced photons of a light photon, number of produced, I mean, the amount of produced light, is that of importance for your studies or for your results? To some extent, of course, but is it? I mean, the number of produced light.
Yeah, well, okay. I mean, there is a loose relation of the total light output produced to the energy resolution, but then again, it is hard to tell for the large volume detectors to some extent, because again, we were investigating also the correlation between total light output and energy resolution. We didn't really find much of a correlation there. But then again, I mean, the design of the detector setup itself was made before any good data was available. So could it be so that with a different medium we could get a similar resolution? Perhaps we need to see.
Yeah. But does it mean that the main contribution to the resolution is from other effects? So
Transport efficiency.
Yeah, yes, yeah. I mean, we will come to that, of course. I already said that. Good. Okay. Then you talk about, I mean, these things that you always talk about when you discuss detectors, the interaction of gamma rays and charged particles with matter. You talk about, perhaps it's I mean, the wording, I mean, and normally it's talked, but did you say inelastic scattering of charged particles on electrons?
Yes.
Yes. I mean, looking at the charged particle and the electron, can there be any inelasticity?
In principle, that's a complicated question.
Okay.
That depends if you're talking about a free electron or bound electron. If you're talking about, it depends on the energy range. Depends on what we scatter on electron. Is it a fully ionized particle or is it partially ionized particle? So some elasticity in some sense can be presented.
Yeah, it's written like this normally. I know that. Then you have presented the Peter Bloch formula, and now I have really a problem with the units. I must say.
Right.
I mean, so it's just a detail, of course. I mean, but if one would like to use the formula as it stands, one of course has to know what to put in, which numbers to put in. And you're not, I mean, you're not defining the numbers, all of the numbers in that formula in the text. So, but for instance, there's a capital A in the formula.
Mass number.
Yes, I mean, that would be the normal definition of A. I mean, the number of neutrons plus the number of protons.
Yes.
In a nucleus. But I would say probably it's not in this case.
Really?
Because I will not get energy per unit path length by putting in a number for A, actually. Because there's a rho in the okay, it perhaps depends on what rho is also in this formula. But there's a kilo in the or mass in rho which never disappears from the formula. And you don't want to have that, I suppose.
Yes, that's a good question. No, still I would say that Z and A are the numbers, and yeah, rho could be defined. That's a good question. How it is defined exactly here. Well, in principle, it should be kilograms per, I don't know, meter cubed.
Yeah. Well, I'm not sure really, but I think one way to solve it would be to say that A is the molar weight, I think it's called. The weight per mole of the, which is close to A, of course. I mean, this number A in some units. Okay, and because then I think it would be correct, the numbers that you would calculate from it. Okay, let's not stop there with this thing, I think. Okay. I want to continue actually in chapter 4 now. Yeah, perhaps one should actually. Well. Let's stop actually at in chapter 3 when you discuss the emission spectrum, the photon emission spectrum in cesium iodide and doped with thallium. It's in principle figured page 37. I mean, you're talking about slow and fast components in the emission. I mean, in order to separate, for instance, protons from photons,
Yes.
you have the slow and fast components. Does it mean that there is 2 decay times present in the emission spectrum?
In the emission spectrum, not necessarily. Because even in pure cesium iodide, we still have 2 components. There is still this difference between free electrons and excitons. The excitation will be not on the dopant center, like it will be on the some peculiarities of the lattice, like some, I don't know, some defects of the lattice.
Yes.
So we will get a different emission peak, but it will not necessarily be related to the time of the excitation, because still there's the excitation from excitons and the excitation from free electrons.
But if it's not time dependent, how can you separate those? I mean, when you take the fast and the slow.
No. What I'm talking about is that you cannot see the slow and fast component in the emission spectrum. Yes, but sure, still in the emission flash, there will be a fast and a slow component.
Okay, yeah. So, yeah.
Yes, but the excitation comes from the pretty much the similar excited state of the defect or I don't know, or the impurity or whatever. It is the excitation from the same state, but with different times. So the emission, we cannot see it in the emission spectrum, in energy spectrum of the emitted light.
Okay, so that is the same. Okay. But what are the decay times of the emission in the scintillator?
Well, this depends on the scintillator itself.
Yes, I mean for this cesium iodide.
For cesium iodide, this slow component is few microseconds, and fast component about below microsecond.
Okay, yeah. And is the doping affecting this relative intensity of those 2, or not?
This is a good question. In principle, it shouldn't, but it is a complicated process. One could expect, I would say, a quenching depending on this concentration, and at the low concentrations. In principle, one might expect some dependence, but again, I mean, it's hard to estimate because we are talking about quite complicated processes.
Yeah. Is it temperature dependent?
What is
the relative intensity between the two?
It might be so. Yeah, absolutely.
Yes. Yeah. Okay. Good. I think we jump to actually chapter 5, which is, I think, part of the main story here. Let's see. Okay. Yeah. First thing that always, I mean, annoys me. I don't know. One construction of 2 words, and it's inverse kinematics, which I don't like.
All right.
But perhaps I'm the only one. I don't know. But what is non-inverse kinematics? Before we invert it, I mean, what?
Okay, we are talking about reactions. Yes, well, as a standard, okay, if you're talking about P2P reactions, it is a scattering of a proton beam on a target. So, and if you're talking about inverse kinematics, it is the other way around. We scatter not a target, but we select a beam of a radioactive beam of selected isotope, and we scatter it on a hydrogen target. So in that case, it is inverse kinematics.
So it has to do with the mass of the target relative to the mass of the beam.
Yes.
Is that? So all the time when the mass of the beam is larger than the mass of the target, it's inverse kinematics.
Well, okay. I mean, one could also maybe relate it to the transfer momentum from the lab system to center of mass system, something along those lines.
Yeah. Okay. Yeah. To me, it's a strange construction, I would say, and it's not Lorentz invariant. This notation.
All right.
If you would move fast parallel to the beam or opposite way to the beam, you would change the relation to say. Then the beam would become the target, and the target would become the beam. But okay. You don't understand what I mean. It's perhaps too philosophical. Okay, but then I have said that we continue instead with the more important stuff. You say that you have optimized. I mean, you're optimizing the properties of the Khalifa detector, and you do it with respect to this spectroscopy mode.
Mm-hmm.
But then there is this other mode, and you also mentioned it here. But what is the? I mean, when you run it in the other mode, what is the difference? I mean, is there a switch somewhere that you?
Yes, but basically it is the integration time in the preamplifier.
Okay. Yeah. Good. Then I understand that there is a way to I mean, from the outside to say, okay, now it's this mode, and now it's the other mode. When you describe the Khalifa setup, I mean, there are different parts of the setup. In the forward direction, there's this combination of scintillators. I mean, you don't discuss it very much more than because you're not. That is not the part of your work, so I understand that. But then in the mid, I mean, there's in the range between I think 20 or something like that to 43 degrees. There is the only cesium iodide, I think.
Yes.
But then you call it intrinsic phosphate. What do you mean by that?
Yes. So by applying a specific analysis of the shape of the signal, we can expect a phosphate-like behavior from a detector. In principle, to some extent, it also could be related to the barrel itself, which was of the major focus of our studies. But yeah, it also the IFOS part of the colorimeter, it is rather long. It is a rather long one. So in principle, the long detectors from the barrel part can be also called intrinsic phosphate.
I mean, is this about the separation between photons and charged particles? Yes. Okay. Yeah, then I understand it. So in principle, you do that also for the whole calorimeter.
Yeah, sure.
Yeah. Okay, this was about the decay time that we have discussed. Okay, and we also discussed the relative intensity in the fast and slow. I mean, if that ratio depends on something more, and we are not. I mean, it may, as you say, yeah, even if it's not clarified here. You talk about the decision how to shape the geometry of the scintillators. I mean, how wide they should be and how long and so on. And you have in equation or in figure 5.4 and equation 5.2, you discuss the sort of maximum extent of the scintillator that you want to have in terms of the Doppler reconstructed energy, to say. In that equation 5.2, you have this delta theta. How would you interpret? I mean, the delta E there is the full width half maximum of a peak in that equation. So that means that from that, I suppose, so from that you can calculate this delta theta, which you have then presented in figure 5.4. Yeah, for different delta E's, or delta E's divided by E. So delta theta would then be something like a full width half maximum of something, or how would you?
Well, okay. I mean that here delta theta is uncertainty of measurement of the angle of the incoming particle.
Yes.
So in principle, it relates to the acceptance of the detector unit, detector module.
Yeah. You have also you have plotted some of the detector crystal, different crystals in that figure 5.4. So there is a so you can read off the delta theta from some of those crystals there in the figure. And that what is that delta theta then? Is that theta 1 minus theta 2, so to say? The cover, I mean
yes, yeah, well, okay, I mean here we are talking about it's not a solid angle, it's just an axial angle.
Yeah.
So yeah, it is a difference between like opening angle of a detector and like closing angle of the detector.
Okay, so it's in principle the opening angle of the crystal. Okay. Yeah, the question is if that is how one should interpret delta theta in 5.2, I think. But perhaps it's I mean, the standard deviation of a distribution. I mean, because here you would probably say that okay, we have a flat distribution over this detector surface, and then the standard deviation of that angle that you cover is not the width of that detector. It's rather that the width divided by a number, square root of 12, I think, for a flat distribution.
Yes. Okay. We are talking about approximate approximate relation between.
Yes. Yeah. Okay. I don't think it makes any difference in practice, but okay. But I understand. So that the width of the detector is really optimized versus, in principle, this blue curve in the figure. Yes, that's good. And then you say that you have that is the maximum, so to say, width of the detector. Then you say that there is this you don't want to go use a smaller width than the something related to the Molière radius. So what would be the problem if you?
Yes, so this has to do with the efficiency of the Edbeck procedure. In our colorimeter, we group the detector modules by 4 in carbon fiber pockets. So between those four detectors, we can perform the energy Edbeck procedure with a high efficiency, because we have very few dead material between them, only the reflector maybe. But between these pockets, the efficiency of the Edbeck would be reduced. So this is the reason why we need to keep a certain lower limit on the width of the detectors, just to make the pockets themselves large enough, which in turn reduces the dead material between the total amount of dead material in the setup.
But yeah, I mean, when you have detect an event, so to say, where you have a signal in one of the detectors, would you then say that, okay, the emission direction is the center of that detector? Is that, I mean, in an analysis afterwards? I mean,
well,
or will you use if there is information from the surrounding detectors to more precisely?
we can, yes, well, okay, I mean, we can, first of all, we have the multiplicity of an event, and then we have the time of the event, and from the time and multiplicity, we can relate back to the detectors. So, yeah, and also, well, yes, the most important part is the time. So from the time coincidence, we can get the elements which are activated by the same event, which also relates not only to the electromagnetic showers, but also the Compton scattered gammas.
Mm-hmm.
Yes, and from that we can reconstruct it back.
Yeah. I was also thinking about. I mean, you want to know the direction of the photon, of course, in the experiment, in order to be able to Doppler correct and stuff like that. So if you have a Compton scattering, and that's quite a common event, of course, that you have a Compton scattering which goes into the neighboring detector. So how would you measure the angle? Yeah. I mean, if you have two detectors involved in an event, what would the emission angle of the photon be, say, when you reconstruct it?
Yes, well, the emission angle is yeah, a good question. So to reconstruct, to perform the Doppler correction, we care about the angle of the first incoming gamma. Yes, is it possible to resolve in time the Compton scattered gammas? A good question.
Probably not, I would
Probably
say,
not.
but I'm not completely sure, of course. But it's a quite short time between them.
Yeah, sure. So
they're quite close. So would that add then an additional uncertainty in the theta, so to say, which may?
In principle, we could maybe hope that if we have a photopeak event with this and that energy, and then if we reconstruct an energy from a Compton event with relatively same energy, we can perhaps say that the direction of the incoming gamma, the first gamma, was the same as the photopeak event. That could be, I don't know, one way to get the direction from the Compton scattered event.
Okay, I'm not completely sure what you mean, but yeah. Anyway, I think yeah, there are ways perhaps to handle this somehow. I mean, okay. Let's continue. Yeah, you have so that was about the width of the detectors. What the length of the detector? Just a question. I mean, you write on page 57 that, for instance, at an opening angle or at the angle 43 degrees, incoming beam with 700 MeV per mass unit gives a proton energy 319 MeV. What is the assumption behind that for proton energy? I mean, I suppose in principle, proton can come with different energies in that angle, not just one energy.
Yes.
So there must be a specific kind of process that you...
Yes. We are talking about P2P reaction.
Okay. So it's really a nucleon collision in principle.
Yes. Nucleon.
Yeah, okay. As if the nucleus was not there at all. I mean, yeah, okay, good. Yeah, then I understand that number. Perfect. you have the readout of the light is that's also this chapter then with APDs or large area avalanche photodiodes. Why do you not use photomultipliers?
That's a good question. Well, one reason not to use photomultipliers was the possible stray magnetic fields from the dipole. Yes. Another thing about avalanche photodiodes is that they have a rather good quantum efficiency. It is rather flat, and in our case, we are talking about 80–84%. So this is one thing. And initially, there was a consideration that by increasing the total area of avalanche photodiode, we can increase linearly or almost linearly the energy resolution of the module, which was happened to be not exactly true. Yeah, but then again, I mean, all these assumptions they were made before any data existed as to the spectroscopy ability of large area avalanche photodiodes. Yes, but still, what we get is the resolution from these APDs is comparable to the PMTs, which we would use. So one good thing about APDs, though, is that when you stabilize the gain with respect to temperature, they are more resilient. So, and you don't really care about, you don't really need to use all the voltage dividers. So they're easier to handle.
Okay, yeah, good. But the higher quantum efficiency, I mean, you have said that the photon statistics is not particularly important. I mean, that you have high photon yield or photoelectron yield in the cases, so perhaps the
yes, now we know.
Yeah, okay, good. There are other factors that are more important, but if they are easier to handle, yes, that's of course good. But I suppose there is a fringe field that may affect the PMTs if you would have had PMTs.
Well, one could say that we could also shield the PMTs, and then we could care less. But yeah, well, I mean, I guess it is a good step forward, because before there was no need to use anything other than PMTs. Okay, for spectroscopy, mostly people use PMTs, and now we can. Now we know that we can, with certain limitations, use also large area avalanche photodiodes. And yeah, I guess that is just a step forward, to the next generation of all setups like that.
Yeah, good. Okay, let's go into the more detailed things. I will try to skip some of the questions, I think. But anyway, chapter 6, which is then about, I mean, all these empirical investigations that you have performed, which is quite impressive, I think. I like this setup that you have, this automatic setup where you check all the, or not all them, but large amount of crystals at the same time. That seems a very good thing, actually. I mean, yeah, there are some things that I would like to ask here about. Yeah, you talk. I mean, the definition of the or the requirement on the resolution comes from the sodium peak 1275, and then you say that okay, this was not used for the measurement of the light uniformity.
Yes.
I think one of the, I mean, what was the real argument to not using sodium iodide? Because the short half-life cannot be a real argument, or?
Actually, I would say that's the major argument, because it is too expensive to buy all the sodium sources.
Okay, so it's an economic question. Okay, in that case.
Yes. Other than that, I mean, it is a nice isolated peak, and also it provides the opportunity to calibrate the detector models with 511.
Yeah, but is it a nice isolated peak? Yeah, isolated, perhaps it is.
Yeah.
Okay, but you will see something more also in the spectrum.
Not in the 1275 region. What we see?
No, not in 12. No.
Yeah, what we see? With good statistics is 511 and 1275.
Yeah, yeah, yeah. If the source is encapsulated, you will see quite a lot of 511. I think.
Mm-hmm.
Yes, perhaps that would dominate the spectrum. I mean.
Oh yeah, sure.
Yes,
sure.
yes,
Yeah.
Okay.
Mostly we see 511.
Yes, yes. Okay, I thought that perhaps would be a complication that you see that you have two gamma rays in the spectrum, but
depends on how close they are.
Yeah, and then perhaps you could also use both of them to compare the uniformity. Actually, if the light in they would depend on.
Sure, but still, it is more convenient to use the scans, the non-uniformity scans with cesium. Yeah. Because it's rather stable with respect to intensity.
Yeah. When you then check the resolution with the sodium source, it seems that you then have the sodium source above the crystal, so to say.
Yeah.
Is the idea then to in principle shine on the whole crystal in principle? With
yes, to get rid of the positional dependency.
Yes. But I mean, in the end, of course, the gamma rays will come from the front of the crystal. Will that change the resolution that you obtain?
Yes, again, depends on the energy. But it is more probable. It is more probable to scatter on the most forward parts of the detector. Still, there is some probability to scatter in the middle or maybe closer to the end. But what we cared in our measurements is to investigate modules as such, independently of the future position and scattering of the gammas during the actual experiment. So if we know that the light output in our modules is even out along the crystals, then it is not of much importance where exactly we detect the gammas.
No. Yeah, I agree. It doesn't matter. I had a question about this efficiency, which I did not understand, and now you said that how you define the efficiency is that in principle that you make some cuts, or in your fit of Gaussian to you leave out tails somehow. The tailing of the full energy peak. Is that the reason to say?
This is what we believe. Yeah. So here efficiency is defined as area of Gaussian fit. Mm-hmm. So with wide peaks, we cannot get a good fit. So
okay. Because otherwise it doesn't seem reasonable that the efficiency would so say be so dependent on the, to me at least, to the light non-uniformity. Okay. Let's see. I mean, then you discuss about the noise, and I think that's good. The noise has a very limited influence on the resolution. Okay, and you show some preamplifier signals there. This kind of standard preamplifier signal is quite a long tail. Some 15 microsecond shaping time or something, or the tail, decay time, yes. And then you also discuss the temperature, and that you have a correction algorithm in your unit. That so you read off the temperature.
Yes, we have at this time we have one temperature channel per amplifier. Sorry, two temperature channels per amplifier, and yeah, so we can measure the average temperature of 16 closed crystals.
Which temperature do you aim at?
The operating temperature is 23, 22, something like that. Yes, we have a flow of nitrogen through the whole setup, and it is an kind of coarse temperature stabilization, and it sets a limit between like 20 something degrees, and in that coarse region we can stabilize the gain with a rather good precision.
Good. Then we come to the energy add back. They were quite interesting figures that you have there. I mean, you say that for that was for the cesium peak, 662 keV peak. Yeah, that adding back from all the surrounding crystals, you increased the intensity by 29.6%. Is that how I should interpret this, the photo peak intensity?
Well, all right. We have investigated an assembly of 4 detectors, but if we kind of extrapolate it to the like 8 neighbors, closest neighbors of a detector, then yes, then we come up with a figure of about 30%.
Yes, yes, good. And in figure 6.9, I mean, you showed these well, scatter plots of the detector where you shine the gamma ray onto, and then a neighboring or the neighboring detectors. And there you also see, I mean, you see the full energy ridge of 662 quite clear there, where you also see that the division of energy between the detector you shine on and the neighbor detector is, I mean, sometimes it's much higher energy in the neighboring detector. That was my question about how you would define the angle in the end, for instance. If you take it from the highest signal, larger signal, then you get the wrong detector, to say. But,
yes.
Yeah. And then you have another ridge there with much higher energy. What is that? I mean,
we are talking about 6.9, figure 6.9.
Yeah, figure 6.9. Yes.
It is background.
That's the background.
But potassium from background.
Yes. Yeah. Okay. It's the potassium peak. Yes. Good. And then about the leakage of photons. I mean, light between the crystals. The figure 6.10. I mean, there's a very small leakage, as you say. That's of course very good. But I was, I mean, the picture 6.10 there to the left was quite interesting, I think. I mean, you see the same deposition of energy in the 2 neighboring detectors there. I mean, because it's a perfect correlation. How I mean, say something about an event that will create this kind of picture. What has happened, so to say, to see those events along the diagonal there?
Yes, that was the curious thing about these leakage measurements. And when we investigated these correlated points closer, we found out that all of them have multiplicity 4 and total energy above 20 MeV. So that was okay. One thing is that since it is more than 20 MeV, then we are out of range we aim to. So this is one thing. Another thing is that the only possible reason, okay, most probable reason is to get some kind of high energy particle from cosmic rays. So we attributed it to muons, which is the most probable.
Yeah.
Yeah. So when we have these muons scattered in in our detectors, then yeah, I mean, one would expect that the energy deposited by a muon in the scintillators should be pretty much of the same amplitude. So
yeah, it's probably what you say, something about 20 maybe, or around
Yeah.
20 maybe. Yeah. But in this case, I mean, for the figure that you see here, I mean, then there the energy deposition in, I mean, one is the plastic and one is the real crystal. I don't know which one is. The real one is 0, I suppose, and the plastic is number 1. Is it so?
yes, plastic is on y-axis and the
Yes,
real one
yeah,
on
yeah.
x-axis.
Because here you don't, I mean, for those events that you see along the diagonal, the energy is limited. I mean, in the crystal 0.
Mhm.
So the high energy must be in some other, in 2 or 3, in detector 2 or 3 then. So the muon must pass through 2 and 3, give a high signal,
Mhm.
and then photons or light is leaking to in the same way to 0 and 1, I suppose then.
Mm-hmm. This okay. Now let me check. All right. So in the setup, the dummy was located in position 1. So we have the like white border between the detectors. Yeah, well, all right. The more light you get in the actual detector, the more light you get in the plastic dummy. I mean, okay, that makes sense because still there is some leakage, and the more light you create in an actual scintillator, the more light would leak out into the plastic dummy.
Yeah, because it's leaked light
Yes.
from 2 and 3.
Yeah.
In this case, yeah. So in 2 and 3 you have a high
Yes.
pulse height, so to say, like 20 maybe or something. Or if you had an, okay, then I understand that thing. Yeah, surface modification. That's of course a big part of this discussion. What in the end, I will not go into so much into detail there. I mean, you discussed also in chapter 7. I mean, how you have lapped parts of a crystal and so on. What in the end, how was it done? Lapping. I mean, now that the crystals are mounted and
yes. The actual procedure is well, okay. The exact details are not known because it is, I would expect, a know-how of the manufacturer. But roughly speaking, we just we just apply sandpaper to the sites in a certain pattern. So yeah.
But that pattern, is that depending? I mean, it's not individual.
No.
It's for the certain shape of a crystal. Then you have.
Yes, it is the same treatment along the whole side. There is no like some particular reasons or something.
Yeah, yes. Well, talking about these lapping and the results of the simulation, perhaps we jump to chapter 7. Perhaps we go back. If you look at figure 7.5 and 7.6, there is a measurement and then there is simulation. And you said that somehow there are trends that are similar in measurement and simulations. Yes, there may be, but I mean there are also some obvious disagreements.
Yes, sure.
I know that this is. I mean, I know we tried things with these PVO detectors. Also, it was quite difficult to get reasonable results from simulations using probably the same simulation package in Giant form. But one thing is, for instance, that in the measurement case, where you have the crystal with no lapping at all, just polished surfaces, then you get the maximum light output in principle. I mean, there are some curves that is slightly above, but so that curve is quite separated from most of the other curves in the top there. But then when you go to 7.6, that curve is there you get the lowest light output.
Yes.
I mean, this is quite
this
big
is,
difference, I would say.
yes. So,
but the shape of that curve is quite similar in both cases. But then how the other things?
yes. So, if you're talking about discrepancy between the actual measurement and the simulation, in the simulation, we did not simulate the angular dependence of reflectivity of the ESR foil, because we didn't know that it is of importance when we were doing the simulations. Now we know that it is, and we have plans to measure this angular dependence. We can, in principle, measure it with the spectrophotometer.
Yeah.
Yes, and that alone could perhaps result in some improvement.
Yeah.
Another thing is that we do not consider the misscattering.
The what?
Misscattering in the simulations, and also it might be not the major contribution, because in principle, would it be so we could perhaps see some sensitivity to the light absorption length. They are not the lengths of misscattering and absorption. They are not exactly related, but we would perhaps see some indication, which we perhaps don't. But yes, still it would be interesting, because the major reason of light scattering in our crystals is probably misscattering. Yes, but to measure it precisely, the length of misscattering is not a particularly easy task. So, but yeah, we are looking forward to measure it as well.
Yeah. Good. I'll go back to chapter 6 actually. Then you discuss light scattering and absorption there, the measurements of the attenuation length, so to say. Yeah, of cesium iodide as a function of the wavelength. What is the refraction index? How large or how small is the refraction index?
About 1.7.
1.7. Okay. It's fairly high. Yeah. In our PVOs, we had 2.2 or something like that, which is quite high also. When you measure this attenuation, just a question, because I don't know how large that effect is. I mean, you measure the intensity on the other. I mean, you shine on one end and then you measure the intensity of the light coming out from the. When you measure the attenuation length.
When attenuation length.
Yes.
Right,
Yeah.
yes.
So you shine on one.
Yes.
One end, and then you read out the intensity in the other end, and then you have to correct for reflection.
Yes.
To say. What about two-time reflection twice inside the crystal? Is that an important effect? Or
we have investigated, and it is on the level of few per mil.
Okay, good. The numbers that you get, they have a very large spread. Is that understandable? I mean, shouldn't there be a number for cesium iodide with this kind of doping, the attenuation length, and you get something between 22 centimeters?
Oh yes,
up to 48
well, yeah. This has to do with the particular manufacture procedures, and the absorption length. It varies between the different batches, and this is what basically brings this spread.
But do you mean it's really different, that the material is different to this aspect?
Yes and no. Well, okay. Now, when we talk about the light absorption length, what we measure with the spectrophotometer is a light attenuation length. It does include actually, to some extent, misscattering, which we try to filter out with applying some absorption material on the sides of the crystal, and comparing the results from like isolated crystal and the crystal coated with some absorption material, we didn't see much of a difference. So, but still, I mean, in principle, when we talk about all this light absorption length and the light attenuation length, what we basically mean is how clear are the crystals. And of course, I mean, from batch to batch, crystals are not exactly the same clear.
Okay, no, I understand. Good. Yeah, let's say something about the thallium doping measurement. First, one thing, PIXE. Is that? Do you know where that is
Originated.
invented or originated?
In the very same university.
Yes. Good. Yeah. So that's interesting to use a technique that is developed here. I will not say so much more about the details there, but about the result. I mean, you get the result where, as I understand, the saying that the doping is homogeneous through the crystal would not be to lie, or?
That's the point with the results of the measurement. We do not see major trends in the distribution with the uncertainty we get. It doesn't rule out inhomogeneity completely. So
No.
yes. So a good answer would be that we need more data. We need more data with less uncertainty.
Yeah. Then just a question regarding in figure 621, you plot there the light output as a function of the doping concentration.
Mm-hmm.
And the concentration that you have is around what is it? 0.08. And you write it somewhere 0.86 or something like that is
Mm-hmm.
percent. Why don't you aim for a concentration around the peak of the light output? I mean, for the reason of this, I mean, then the variation of the doping concentration would not matter. Because then the derivative is zero. I mean,
yes, that's an excellent question. I would myself also prefer that region. Alas, it is so that the negotiation with the manufacturer were made before we realized this.
Yes, yeah, okay, yeah. I mean, I don't know if there are other problems.
Yeah, well, again, I mean, one thing is that the manufacturer can provide these many crystals with this concentration of thallium in such limits with such price. So we could perhaps obtain a limited batch with this and that limitation, but that would be a different price. And we are talking about in the calorimeter, we are talking about roughly more than 2,000 detector units, so it can become quite costly.
Yes, I understand it. Yeah. Good. I think I will come to the end of my discussion here. I mean, in the end, I mean, you seem to fulfill the requirements that you have set up for the spectrometer mode, so to say. What about the other mode? Is that at the same time automatically fulfilled? Do you know
yes,
that?
that's a good question. I mean, I personally did not investigate the energy resolution for the scattered particles, but from what I see, it is much easier to fulfill the energy requirement for the scattered protons than for gamma ray spectroscopy. So shouldn't be a problem. What we really care mostly for the scattered protons is that to stop them in the scintillating medium, and this we automatically fulfill from the length of the detectors.
Yeah. So perhaps a final question. I mean, with the knowledge that you have now, I mean, from all your investigations, if you could start from the beginning with this detector, would you have changed anything in the how you configure the detector or do things?
Yeah, well, I mean, we could perhaps, again, I mean, it's hard to tell. Of course, we could perhaps aim for better performance. But would it be then feasible from the economical point of view is a different question. So, I mean, what we have at hand is a reasonably good and a reasonably cheap setup. So would we aim for better resolution? Okay, yes, of course, we care about resolution. We could perhaps get a better resolution, applying maybe even bigger avalanche photodiodes, maybe introducing more temperature channels. Yes, that would be one obvious upgrade. But then again, I mean, we need to consider how expensive could it be.
Okay, thanks. So my last word would be to congratulate you to a very nice, important work that you have presented. I'm quite impressed with the detailed investigation that you have done that I assume can be of use for other people as well in the community, actually. So thank you very much.
Thank you very much.
Okay, thank you both for an interesting discussion. And now it's time to contact the evaluation committee as to whether they have some additional questions, so to say, from their end. And I only see 2 out of 4 at the moment, but I guess the other 2 will show up in a second. And the kind of question from my end is, do you 3 have kind of predetermined a sequence, or is it open, or no sequence? Okay. Then maybe just to kind of involve people from the outside of the lecture hall, I would like to invite Anne-Cécile maybe to ask her whether you have some additional questions or concerns that you want to double check with Alexander.
Okay, first of all, thank you very much for all the work you've done. I completely agree with the opponent that this was a very interesting read. And I learned a lot myself by reading it. So some congratulations. Well, actually, most of my questions are already asked. It was a very thorough questioning and discussion round. But I do have a small question, maybe. I noticed that throughout the text, when you talk about transfer reactions, you consistently say that you only populate levels above the Fermi level. So then I would like to ask you, what about pickup reactions?
Yes, sure.
So like helium.
Yes. Well, all right. What I was thinking about when I was writing this part of the thesis is that if we restrain ourselves to the if we are talking about the nucleus of interest, which for a low energy experiment would be the nucleus from in the target, then the population happens only for the states above the Fermi level. For the and for the beam itself, yes, of course, so we can consider as well the pickup reactions.
Because pickup reactions would typically
Yeah, sure.
populate states below the Fermi level, right? So if you have stripping, then you populate above, and if you have
Yes,
pickup
absolutely.
reactions. So the just a bit maybe imprecise to call it transfer reactions, because they do. Transfer reactions include both stripping and pickup. Okay. And then, I had the same question about the PM tubes. But I wanted to ask you, is there a reason for the mix of the different detector types? You have the phosphate and you have the cesium iodides.
Yes. Well, the aim was to get the best resolution at the most important angles, and the most important angles are the closest to zero. That's why in that range of angles we have these phosphate, lanthanum bromide, lanthanum chloride, and for the others, I mean, 7% is good enough.
Excellent. And that brings me to the final question I have. If you had all the money in the world and you could design the best detector in the world, how would you do that, and what kind of material would you use for these kind of experiments, for the R3B setup?
Yes. Okay. If you're talking about this decalorimeter itself, then we would perhaps aim for some very good scintillator still, because I mean, of course, it would be good. It would be excellent to have a germanium detector, but the germanium detectors, they are rather slow. So a very good scintillator would be perhaps the choice, like these lanthanum bromides or something along those lines.
I completely agree. Thank you so much.
Okay.
Okay, thank you. And then, are there any questions from any of you here? Because then I forward the microphone, and then you either pass it, or you pass it either way.
Yes, thank you, Alexander, for a very nice presentation, and indeed, congratulations on the very extensive and interesting work done. And yeah, there have been already extensive discussion of many aspects, but since I'm not from the field really, so I have probably some questions which are kind of a bit more generic also. I mean, one thing which I was wondering, like, what is in general status of the experiments with radioactive beams? I mean, how many facilities are there of this kind, or what sort of experiments are being run there? I mean, just quickly, just few.
This depends on the scale. There is a number of small scale facilities with radioactive beams, but if you're talking about large scale facilities with very versatile radioactive beams production, then in total it is Triumph, Riken, GSI, Ganil, MSU. That's about it.
So it's not a kind of every contribution counts a lot, right?
Yes. Well, I mean, okay. Again, this depends on the level of development of the field itself, and now there is a lot of plans from very different countries to build the fair scale size facilities. Like there are some talks about the China. There is some talks about Russia. There is this project FREEP from the United States. So yes, the field seems to becoming quite hot.
Okay, very good. One thing actually in the very introduction, when you talk about the optical model, and then you use it several times, especially when doing fits, what was unclear to me, how many free parameters are there when you run your fits? Because sometimes I see 6, sometimes 4, but how many are there? Because then you discuss the different different sets of parameters can result in similar chi-square per degree of freedom.
Oh, right.
But when you have very few points and very many parameters, then you may end up with just 1 degree of freedom or something. So So how many parameters are free?
Not sure. Well, all right. Now, if you're talking about the fitting of the parameters of the optical model, then we have two different depths of the potential, and then we have two different diffuseness, the real one and the imaginary one. So in total, it is 4 parameters.
Okay, so it's 4 in general, right?
Yeah.
And how many data points you usually fit with those? Because for example, this figure 2.3 shows like only 5 data points with 4 parameters that will leave you with 1 degree of freedom.
Yes. Well, I mean, the bigger the better. Yes, that's why we were aiming. That's why we were using the Gloria detector, because it provides quite a good angular resolution, and it is also a quite compact detector itself. The challenge with the carbon 15 experiment was that only a limited range, a limited angular range results in any data. So yes, in future it looks like we need to have even finer angular resolution to have a good fit.
All right, and actually, and perhaps one last question about the non-uniformity measurements. I think there, you had this figure. Let me see. I just have to flip through the pages. But first, the formula 6.1, it says NLO, but actually it should be delta
it should
NLO,
be
right?
delta LO,
Yeah.
yes. It is a
that's-
typo.
yeah.
Yes.
Yes, so figure 7.6, yes, and you also showed it in slide 39. So I understand then in discussion in the text that somehow using this figure you found the value of delta and LO, although I can't see how, because in this figure you have like fixed, you have different lines for fixed values of delta and LO, right?
Yes.
So it's not that you measure it there, you kind of define it and then plot the bands. Or how does it go?
Yeah, well, okay. I mean, from the band, we can directly extract the delta LO as a position of the maximum and the maximum and the minimum position of the photo peak.
Yes, but not from figure 7.6.
7.6.
Or
why not?
Okay. So you mean basically you can extract it from actually the
Yes.
points.
Yeah, absolutely.
There. Okay. Okay, so the legend means that this is the value calculated from the points. It's
Yes,
not that something.
yeah, absolutely.
Okay.
Exactly, yes.
Okay. Yeah, I think just let me cross check one more. Oh yes, actually, yeah. One question about Jan 4.
Oh.
Well, not really about Jan 4, but basically the principle, because that's something which is common between particle physics and I think nuclear physics, because we'll use it for our detector simulation. So indeed, you use it to simulate or to design your experiment. Can you think of other uses of Jan 4 except of like design experiment?
A plethora of uses. I mean, starting from, I don't know, like space exploration and ending into like medical science. So yeah, I mean, a lot. So for example, I don't know, I guess one of the brightest examples could be the use of Jan 4 for simulation of the dose in the cancer therapy. So there you go.
But also, I was thinking more like towards data analysis, for instance. When you collect your data from your kind of imperfect detector, can Jan 4 come to rescue in some way?
Yes. Yeah, sure. Of course, we can also simulate the response. Well, okay. Of course, we simulate the response of the detector, but we also can include the digitization part into the simulation analysis. Into the simulation. And yes, that could point towards some artifacts due to digitization.
So in principle, you can use it to correct your experimental data.
Yes.
Okay, very good.
Yeah, so
Let me also start with extending my congratulations for a nice thesis, and also to the opponent for a thorough questioning. I thought I would like to ask some questions about APDs and temperature monitoring and so on. So to start with, you said you had a few thousand crystals. So you have two APDs per crystals. Is that?
Yes, but all of them they sit on the same wire. So in principle, we just double the area. We do not read these areas with different channels.
Just to increase the signal.
Yes.
But then if I go to your page 72, where you quote this number of your parameter, this 3.9% change in yield per degree Kelvin. How does that vary between the different APDs? I mean, I think in the paper also you show the example for one APD. What is the spread between the?
Oh yeah, that's an excellent question. That's an excellent question for the future measurements. So far we have measured one singular APD, and we can compare it to the nominal value. So one estimate of the spread would be the difference between the nominal value and the measured one.
Yeah, I think so. I can say that in my detector that I work with, we had for 10 years ago, I worked on an APD system which had 15,000 APDs or so. And the spread was of the order 0.5 to 1%. So like 3 to 4%, for instance, in this. So I would encourage you to, it's a significant thing to look at. And related to that, when you do this temperature calibrations on your preamp, where you have 16 crystals, is it possible to have an individual correction there? Or, I mean, assume you figure out that there is an individual spread between the APDs. Can you correct for that for the individual APDs? I guess not at the moment.
Not easily. I mean, we can, in principle, measure the temperature field in different environments, and then we can perhaps adjust each singular channel to each singular temperature, but that would be quite difficult with the setup we have at hand. Not impossible, but maybe challenging.
Okay. And then I think you said, what is the, but I missed it quite, but I think you will keep the temperature window around 22, 23 C, but how tight do you think you can keep it balanced over time?
Yeah, well, I mean, as I said, it is not exactly tight because we are talking about few degrees centigrade. But what is important for us is to keep it below 24, because if we go above 24, we can see some artifacts of the gain correction routine. Yes, and below 24, we actually don't really care much. There was a study before we investigated our APDs for the temperature stability. People were changing the temperature from 0 to 23 degrees, and the gain was surprisingly stable. Now we have extended it to 28 degrees, and unfortunately, we see some kinks. Good thing is that those kinks, they are above the operating temperature.
Okay. And can you say also, did you try different APDs, or you have only used this Hamamatsu?
In my work, I used only Hamamatsu. Okay. Only one particular type of Hamamatsu APDs.
So I can say for our detector, we ended up using Perkin-Elmer that was cheaper and had half the temperature sensitivity than Hamamatsu. So it was
good to know.
And I can also recommend, if you wanted to monitor this over time, that you have some maybe like an LED system or SE silicon photomultiplier to keep track of.
Yes, indeed, we have a group which develops an LED tracking system.
So this was maybe a little too specific here, but I would like to ask a final question. Since you mentioned that you had looked at lower temperatures also, and the yield goes up quite a lot there, so you could have saved half the cost if you had run at, let's say, +5 C or something?
This depends. This depends on the costs of the implementation of this, temperature stabilization. So hard to tell. This is something to estimate.
No, I think you did the right choice there, actually, because in our detector experiment, at least there was 2 groups, and one of them decided to cool things, and one decided to basically have bigger, more APDs. And in the end, it was cheaper to have less engineering and less trouble to just have more APDs. So that was a good choice. Okay, so thank you for.
Thank you very much. And now eventually, Magnus, since you have been with us all the time, would you like to ask a question as well?
Yes, I could. I think many questions have been taken already by the opponent. I was also a little curious about the zero P state and these things, and so it's 2 sort of ways to define it. And I'm very happy that you show this spherical Nielsen diagram that comes from Lunds, from Nilsson in 1955. So that I think is really nice to have in your thesis. That was very interesting to read. I had some places you don't define things, and on page 33, figure 3.3, there you claim that you see 2 components, a central core and a halo. That is easy to see, but I don't see it. Could you explain what is X0 and?
All right. Let me refresh. All right. So we are talking about transversal distribution of energy in electron photon showers. Yes. Well. All right. Now, what is shown is that all right, so relative energy deposit at different molar radius, at different radiation lengths. So I would say that the smaller the depth, the more compact is the energy distribution, and then we go and the energy distribution at different molar radius. Now, if we consider the more distant, parts, the energy deposit becomes more spread. So that's why we're talking about the core and the halo.
Okay, thank you. I will not keep a long discussion here. It was I was just curious about page 93. You mentioned Fano factors and Rayleigh, and I don't know how to pronounce it, Mie scattering lengths. And then I got curious because later on you say that you could improve the simulation by including Mie in the chat. What is this Mie scattering?
It is scattering on the small particles, so to say, spheres of certain diameter. And for Mie scattering, we go down to few microns, like 10 microns, something like that. Okay. Scattering of radiation, scattering of electromagnetic radiation on such spheres results in a characteristic shape, which is called Mie scattering.
Thank you, Alexander. Then I think I don't have more questions. Thank you.
Okay. Thank you all. And then I can open the floor for the general audience, and maybe we start off with the audience in the lecture hall. Is there anybody present here who would like to ask a question? Bob?
Thank you. Yeah, so related to the doping, now you said you can't rule out any inhomogeneity. You need better statistics. That was made very clear. But obviously there's going to be a level below which, or a level below which inhomogeneity is not really going to have any effect on your results. So do you have any feeling for where this is? And further to that, how much would you need to improve the statistics on your measurement by to get within that range?
This depends. I mean, already now with the data we have, if we talk about not light output non-uniformity, but energy resolution, we see that the uncertainty we get provides us with a widening of 0.5% of the photo peak, which is perhaps a reasonable number. Still, it would be of interest to get closer to the actual number of 0.22. So for that, I would say we need like maybe 4 times more statistics, hand-wavingly.
Yeah, thank you.
Okay, anybody else in here? Okay, I don't see any hands here, so then I'll go to the computer and have a check in the Q&A, so question and answer in Zoom. Currently, there are no open questions. So, but if anybody out there, then please open the box and type a question, and we will wait for a few seconds here, whether anything shows up. I guess that's the procedure. Okay, so nobody has been typing anything, so there are no open questions, which implies that I will close the formal part of this dissertation act. I'd like to thank again everybody involved, and I would like to invite the opponent, evaluation committee, and the supervisors to the neighboring seminar room H2 422. For further discussions, and otherwise, eventually Alex is collecting people in the lunchroom, I presume, I don't know. And then, yeah, thank you very much for coming, and have a nice day and weekend. And eventually we see each other again in a few minutes in the B200 corridor. Thank you.